chapter 14 is on linear regression. And what we mean by this is that if we have any data, in general, it's experimental data, and we want to represent it by an equation, we have the possibility of representing it by linear equation, by quadratic equation, by polynomial equation. So we have several possibilities. In this course, we will learn how to come up with linear regression in order to represent experimental data by a linear curve fitting. And then in the next chapter, we will go over nonlinear regression techniques. So the objectives of this chapter is to use the least squares regression to fit a straight line to measured data, and to use linear regression for nonlinear trends. So we will see that even if we have a nonlinear trend, we can do linearization of the function so that linear fit will work. So we have several examples in which we have nonlinear trends that can be presented by a linear regression fit. So to start with, you know that in general, whenever we do experiments, we just get discrete points. We don't get functions. But if we need to give a general result that can be extrapolated, so even, for example, here, if you are conducting the following experiment, you have a certain occupant held by a cable, and we put a airflow blowing on it. So under the effect of this airflow, we can measure the force acting on the occupant function of the velocity of the airflow. So we should subtract from this force the weight of the occupant. Then we can find how the force acting by the fluid on the person will change with the velocity. This is a possible experiment that we can do. And as expected, higher is the velocity of blowing air with the fan, higher will be the force acting on the occupant by the airflow. So here, for example, if we conducted experiments with velocities of 10, 20, 30, 40 meters per second, let's say, 50, 60, until 80. So we are just doing for each 10 meters per second, we are considering a point. So 0, 10, 20, 30, 40, 50, 60, 70, 80. Now, if we are interested, for example, into knowing what will be the force if I have a value of 65 for the velocity, or if I have a value of 75, and I don't have experiments performed at these points, I can say from the points I have, I can come up with a certain fit. It can be linear, it can be quadratic. It depends on the points, how the points are, the behavior of points. So sometimes from just when you put the points, you might decide if it's look like they are close to a linear profile, you say it's better to do a fit using just a linear function. If it seems that it's follow a parabolic behavior, then you say I will use a quadratic fit. Okay, so sometimes the points will suggest to you which type to use. And plus, we will develop techniques to tell us the degree of accuracy, and what is the error involved, and if this fit is acceptable or not. Okay. So to start with, we will define how to do a linear fit. But before doing this, we need to do statistics review, because whenever we talk about experimental data and we want to do fitting, we will involve statistics. So here, you know that in general, for example, if I am performing an experiment, in order to determine the coefficient of thermal expansion, then what I will have to do is to vary. For example, I know that from thermodynamics that this thermal expansion coefficient is given by the following formula. If I have a certain material and I take a specimen of length L, and I subject this specimen to a raise or decrease in temperature. So here, if we talk about expansion, then I should increase the temperature. So if I impose a certain increased delta T on the material, knowing the initial length of the specimen, I can compute what will be the increase in length due to the thermal expansion. And delta L is given as alpha times L times delta T. So here, if I want to get alpha experimentally, I need to calculate what is delta L for different values of delta T. And this will allow me then to come up with a coefficient alpha. Okay? And since experimental work is always prone to errors, so I can have, for example, measurement errors in delta T, I can have measurement errors in delta L. And this is why I might need to repeat the experiment several times to get a certain average value for alpha. Okay? So for example, if you conduct this experiment several times on several days, okay, then I can summarize my results by saying that I will consider all points, and I will consider that alpha can be taken as the average between these measurements, and then I consider that alpha bar is summation from 1 to n of alpha I over n. This is the arithmetic mean, which is the average of values obtained experimentally. Okay. Now, even if I get alpha bar, if I want to make sure if my experiments were consistent or not, I can measure what is called the standard deviation. The standard deviation will give me an idea of how much my points are differ from the average value. So if I have points that are far apart from the mean, this is not good. Okay. So how to compute this? I can compute this using the standard deviation, which, if you want, is a measure of the error involved. Okay, the standard deviation is calculated as the summation from 1 to n of alpha I minus alpha bar squared. So higher is the standard deviation, higher is the deviation between the mean and the experimental data, and lower is the standard deviation, then my prediction of alpha is more accurate because all measurements will lie within a small interval with alpha bar. Okay, so we can represent this graphically to see the difference between a high standard deviation and a small standard deviation. So here, for example, the standard deviation also is, if you want, an average of error. It's the average of error squared, because I might have here points within the interval and I still have points far from this interval. Since Sy is defined as like a summation of errors, so for these points here you have very large error, for these points you have small error, so this can be as somewhere in between. So as you can see here, you have points that are far apart from the mean. This will lead to high standard deviation. While if your experiment was more accurate, then you can come up with a smaller standard deviation, and then all your measurements will be within a tight interval about the average, and this is good. So this is of course it depends on the accuracy you want. So higher the accuracy, lower is the standard deviation desired. Now from this idea we will define the error in case of a linear fit. Okay, so in a similar application, just now instead of comparing with the mean, when we do an equation fit, we compare with the value at the straight line. So our purpose here, this is our fit. We want to try to determine the equation of this fit in a way to minimize the total error. So for each point of measurement, I have a certain error between experimental data and the fitting point. So for example, at this location, this is Y fitting here. And this is the difference in between. At this point, this is the difference. At this point, this is the difference. So I can define the error, okay, at any point. The error is equal to the actual measurement data, yi, minus the value of the fit at same x, at same xi, okay? And since it is at same xi, so here, if I consider this is my xi, for example, for any xi, I have yi experimental is this one. This is yi. And y fit is y corresponding to same x. So this is y fit at I. And then I can define the error. At the end, I will take the absolute value of the error. I can take it as yi minus y fit or y fit minus yi. It's not a problem, since I will consider at the end the absolute value, because I will do it also square. I have several possibilities, as I will explain later, but here we'll take ei square. So this ei can be calculated as the difference between yi and y fit at I, and y fit at I can be expressed function of xi, since y fit at I will follow this equation, since I am considering the point on the line. So yf at I is equal to a0 plus a1 xi. And now I can say that the error at I is equal to yi minus a0 plus a1 xi. And what is my purpose here? My purpose is to minimize the total error. By summing errors at all points, I can sum the error, absolute value of error, I can sum the error square. So all of these techniques can work. Like in condition number, when we define norm, we have several ways to define the norm. Okay, here also, we have several ways to define the error. So the objective is to minimize the error using least squares regression. Least, because we want to do minimum, we want to minimize the error. Square, because we will take summation of error square. Okay, so here is a definition of the total error. So we will define the sum of residual as SR equals to summation for I going from 1 to n of ei square, where ei can be replaced by yi minus a0 minus a1 xi square. And as you can see here, as I told you, it's one way to define the error. You can tell me why I didn't take sum of absolute value of the error. This is also a possibility. You can also take sum of absolute value of error cube, or sum of error to the power 4. All of these can be techniques to define error, and then I should minimize it. But we have seen that each method has its own advantages and disadvantages. And for our applications, engineering applications, this is the most commonly used method, which is the least square regression. Okay? Now, so we will proceed with this method. Now we define the error. And as you can see, this error is function of two unknowns, a0 and a1. Once I get a0 and a1, then I know what is the equation of my linear fit. Okay? While for yi and xi, I have them because I did experiments, and I have all values xi and yi. So the only unknowns here are a0 and a1. Since I have two unknowns, I should write two equations. And what will be these equations? What do you think the equations that I should use to minimize SR? When we ask you about the minimum of a function, what do you do?
Derivative.
Exactly, the derivative. And since SR is function of two variables, a0 and a1, then you should do the partial derivative of SR with respect to a0 equals to 0. This will give you a first equation. And the second equation will be obtained by doing del SR by del A1 equals to 0. So this will give you the second equation. So now you will end up with this is equation 1, this is equation 2. I will then solve for my two unknowns, A0 and A1. So now let us proceed together and derive SR, first with respect to A0, then with respect to A1. And now just before doing this, as you can see here, this error SR is similar in concept to the standard deviation. But the only difference is the standard deviation compare the deviation of these values, the data we have from the mean, while SR represents the deviation of the data from the fit, from the equation line, from the linear equation we have selected for fit. Okay. So now our purpose is to find the coefficients A0, A1, which defines the equation of the linear fit. This is why we will first derive SR with respect to A0. When I want to derive with respect to A0, I will consider here that all remaining things are constant. Okay, so if I have, this is a function of A0, but I have this function square, so I can call this function U. Okay, you know that when you want to derive U square, what do? You do 2 times U times U prime. Okay, and now since you are deriving with respect to A0, then U prime will represent the derivative of U with respect to A0. And as you can see, when you do U prime, this is a constant for U, and A1 is treated as a constant because you are doing the partial derivative with respect to A0. The partial derivative with respect to A0 is just -1. Okay? So now, all you have to say that the partial derivative of SR with respect to A0 is equal to -2 times U. And what is U? U is this function, which is yi minus A0 minus A1xi. Okay? And since here, of course, since you have summation, then you should do del SR by del A0 is the summation of -2U, summation from 1 to n. And now, replacing U by its value, which is yi minus A0 minus A1xi, and knowing that since -2 is a constant, I can take it outside of the summation. So now, in order to have the derivative of SR with respect to A0 equal to 0, I just have the following condition, that summation from 1 to n of yi minus A0 minus A1xi, this summation should be equal to 0. This is equation number 1. Equation 2, I get it from deriving SR with respect to A1. So now when I want to conduct the partial derivative with respect to A1, I do the same and same concept. So first I name this function U. I say that the derivative is 2U U prime. Now U prime represents now the partial derivative of U with respect to A1. Okay, so now I have that, and if you want to be accurate, ما بنحط U prime لأنه U prime هي total derivative, so we should decompose it. يعني we should put U prime with respect to what? We should put with respect to A1. Okay, so here when I do the derivative with respect to A1, this is constant, and I just have then minus xi. So del U by del A1 is minus xi. And now I can say that the derivative then with respect to A1 is minus 2xi times U. And again, since I have a summation, so the derivative will be summation, because you know that the derivative of the sum is equal to the summation of the derivatives. Okay, so I have, since -2 is a constant, I can take it outside of the summation. And then my final result for the summation of del SR by del A1 is -2, which is the constant I took outside, times, instead of the summation, I have xi times yi minus A0 minus A1xi. So now, since it's equal to 0, I can simplify -2, and then this will be my second equation. Now, in order to solve for A0 and A1, I cannot keep the summation as it is. I should expand my summation. I should do summation of yi minus summation of A0 minus A1 summation of xi. Let us do it together in next slide to see how to transform these two equations to a system of two equations with two unknowns with clear defined coefficients. So first, I will start with the first equation. I will expand it, okay? All I have to do is to divide the summation. So I say that this term is equal to summation from I to n of yi minus summation from 1 to n of A0 minus summation from 1 to n of A1 xi. And now I will do analysis of my terms. First, since xi, yi are all given, so this term can be calculated from the data I have. Sum from 1 to n of yi. All I have to do is to sum all y. And then I can call this term sy, okay, which can be calculated from the given data. Now, A0 is unknown, but A0 is a constant, so I can take it outside of the summation. And then I can replace this term by A0 times summation from 1 to n of 1. And summation of 1 from 1 to n is equal to n, because I do 1 plus 1 plus 1 n times, so I get n, okay? And then I can replace this term, this summation, by n times A0, where n represents the number of points, okay? This is the number of points of my data. Finally, for the last term, what do I have? I have summation from 1 to n of ai xi. Ai also here is a constant coefficient, so it will not affect the summation. I can take it outside of the summation. And then I just have minus a1 times summation from 1 to n of xi. And this term also I can assess it because I have the data, and I can call it as summation of x. So once I do this development, I got now a first equation where sy, sx are known, n is known, and the only unknowns are a0 and a1. This is equation number 1.
Doctor?
Yes, Karen. Yes, Karen.
I think, no, I don't know, because when we do a sum of unknown, we cannot put, can you repeat? I've understood what I mean. The sigma of A0, how did it become N A0?
Okay. هي كارن هي A0 unknown بس عندها one value صح أو لا؟ It's one value. It's a constant. صح؟
Okay, yes.
يعني أنا إذا بقول لك A0 can be any number بس it's one number. بما إنه it's يعني أنا إذا بعمل لك summation from I equal from 1 to 5 of 2 ما فيك تاخدي 2 لبرا وتقولي إنه هي 2 times summation from 1 to 5 of 1.
Yes.
اوكي نفس الشيء هون A0 is a constant بس ما بعرف الفاليو تبعها. I can take it outside of the summation. اوكي ساعتها بيبقى لي جوا او فيك تخليها بقلب السميشن. اذا انا بعمل لك A0 from 1 to n times يعني عندك A0 plus A0 plus A0 n times شو بيطلع لك الريزلت؟
n times A0.
فيك تعمليها in both ways. فيك تخليها جوا وفيك تطلعيها لبرا لانه it's a constant بيبقى لك summation of 1. اثنيناتهم بيعطوك انه the result is n times A0. اوكي
Yes, والسميشن لحد دكتور.
اوكي summation لحد نفس الشيء. انا A1 كمان constant ففيني اطلعها لبرا السميشن. شو بيبقى بقلب السميشن؟ بيبقى sum of xi. هيدي بجيبها من الداتا اللي عندي اياها. يعني انا اذا بعطيكي table of data points 1 2 3 مثلا والواي تبعهم هن 2 4 6 شو بتكون sum of xi؟ This is xi. This is yi. summation of xi بتكون 1 plus 2 plus 3 يعني summation تعطيني of xi تعطيني 6 والsummation of yi 2 plus 4 plus 6
12.
تعطيني 12. ساعتها I replace in this equation summation of yi by 12, summation of xi by 6, and n شو بحط مطرح n؟
3.
3 exactly, because n is the number of points اللي هو 1 2 3. okay.
Yes, doctor.
Okay, now we will proceed in a similar way to get a second equation. إذا بتتذكروا تاني equation كانت del SR by del A1. الفرق الوحيد إنه هون كان في زيادة XI جوا. هذا الفرق الوحيد بين two equations. يعني كان في minus 2 summation from 1 to n of xi times yi minus a0 minus a1 xi. So let us do it together. إذا بحط هون xi, when I do the expansion حيصير عندي summation from 1 to n of xi yi minus summation from 1 to n of xi a0 minus summation from 1 to n of a1 xi square. هلا for the first term all I have to do انه انا عندي x و y بدي زيد line. يعني انا الاكزامبل اللي اعطيتكم اياه هلا 1 2 3 4 5 6 اوكي. هيدي xi هيدي yi. I should add a line to this table to compute xi times yi. يعني اللاين الجديدة هون حتكون first 1 times 4 4, 2 times 5 10, 3 times 6 18. I got xi yi. Now I do the summation of يعني على طول بدي أزيد آخر شيء summation اللي هي 4 plus 10 14 plus 18 32. يعني هيدا الترم I can replace it then by 32. okay. تاني term هو sum xi a0. كمان since a0 is constant I take it outside فبيطلع لي بدل هون n بيطلع لي a0 times I should add to it times summation from I going from 1 to n of xi اللي هي already لقيتها بالprevious step. okay. وfinally for the last term عندي a1 constant تطلع لبرا. So I have minus a1 times summation from 1 to n of xi square. So now what I should do, I should add a line to my table. هتكون الline xi square. So I have 1 for the second term 2 square 4, for the third term 3 square 9, and now I do the summation 1 plus 9 10 plus 4 14. I replace some xi square by 14 and then I get my second equation. Okay, let me check your questions. Yes, Hassan, values of sx and sy are known in the table. Okay.
Yes, doctor.
Okay. Okay, so this is how we got two equations with